Hello everyone, my name is Tobias Schwartz, and this is a joint work with my colleagues Sioutis and Diedrich Wolter. In particular, this is a short teaser talk for our challenge paper towards HTN planning as Constraint Satisfaction Problem. Let me start with a motivation. In recent years there have been a lot of efficient ways of solving HTN planning problems. And recently in particular, there have been a lot of encodings in propositional logic, SAT encodings for HTN planning. We argue, however, that HTN planning is subject to a lot of natural constraints just from the hierarchical structure, the ordering of subtasks, some numeric constraints, just to name a few. And all of these constraints are sometimes hard to express in propositional logic. So we argue that it may be more natural to formulate the HTN planning problem as a constraint satisfaction problem. And there have been proposals similar to ours. So for example, there have been ZSP encodings for classical planning already. And even for HTN planning, there has been this meta CSP formulation where they had multiple CSPs for various forms of information. In contrast, what we propose is to use one single CSP, similar to how it is done in the classical setting, and implement that in the hierarchical environment using some ideas from recent incremental SAT encodings. Some short preliminaries. We specifically propose to use qualitative constraint satisfaction problems, which are usually used in the qualitative temporal and spatial reasoning environment. They are pretty much like normal classical CSPs, but for infinite domains, and they're usually reasoned on in qualitative constraint networks or short QCNs. In particular, we propose to use the interval algebra, or more precisely a part of it, consisting out of the equality or the inequality being basically all the base relations without equality and some ordering constraint before or after. You can see a short example in a qualitative constraint network where you have a task A and that is before task B, and this task B again is before task C. And you can see by just reasoning, you can infer that task A also has to be before task C. Just in short, how do we vision our HTN planning constraint model? I will just sketch a few ideas. For more details, please come to our poster then. So here I have two snippets from HDDL, and this is an action drive. And here this is a variable mapping. So we have a variable L1, which is a location of the type. And we see here in the problem file we have three certain locations. And then we would model this in a constraint network. So you can think of this constraint network being like a state where certain variable bindings are true. It is only that using our constraint network approach, we're basically lifting from a grounding by doing those precise mappings only when necessary, right? So in this current configuration, we have EQ or not equal, so basically the universal relation from this L1 to all the particular ground objects or ground locations there are. And now the idea is that in the search procedure that is solving the constraint network, we prefer the equality constraint over the not equal. What does that do? Well, it forces that we only have at most one variable binding to precisely one of them by forcing through the path consistency algorithm that the others become not equal. In short, those similar constraint networks, as said, are similar to state representations, and we say with an action application we create a new state, here mapped with a k, so the lower index k is the number of action applications, the length of the final plan, if you will. And you can see how when applying the action drive here, we are changing the equality constraints from the truck being at location 1 to at location 2. And then we have a second component, and that is the hierarchical structure. We do this by an incremental idea. So we have an I counter, and this is incremented for each method decomposition. So we have various options to decompose certain methods or certain tasks, and here we'd add a lot of new tasks to the constraint network, and whenever we have tasks, we would resolve them later on. This is just all for now, some open challenges, this being a challenge paper. You can see we dynamically create new constraint networks, and this may or may not result in a computational blowup. Our assumption and hope is that the constraint solver can prune inconsistent configurations efficiently. Furthermore, we have variable mappings that are restricted by their corresponding type, but in case we don't have types, we might have or result in inefficient mappings to all ground objects. We also believe that our QCN representation fits the lifted HTN planning formalism from HDDL nicely, but it could very well be that we still need the propositional representation as usually done by grounding before action application. And finally, we also want to refine our encoding such that state-of-the-art constraint solvers don't have to be adapted like it is now done with the search procedure. For more, please visit my poster and I'll explain happily all further details, and we can discuss those challenges and more. Thank you.